Okay, we're going to be talking about this theory. Now, before we do so, do I have anyone from Dr. Roche right now? No, right? Everyone's Dr. West? Okay, that's good. So now, before we even start drawing any diagrams or looking at anything, on this page where you have a little chart, that's going to be your little cheat sheet for this topic, okay? That's going to guide you through how to draw your different energy diagrams and all of that. Now, specifically, this theory, we're only going to use it for any conjugated systems, okay? So again, that means that you have a little pattern where the carbons are sp2. So if we look at 1,3-butadiene, we can see that the molecule, in fact, it is conjugated. So of course, we can use this theory. So in this case, how many sp2 carbons do you see? 4, exactly. Meaning that we have 4 orbitals. So remember, your key is going to be that the number of sp2 carbons is going to equal to the number of orbitals. Okay, that's going to be your key. Now, based on that, that's how you're going to start drawing out the different lines that you see in here. Those are the different orbitals that you have. That's why there's 4 lines. And once you start labeling them, you always start from the bottom to the top. So that's why bottom one is pi 1, and then pi 2, pi 3, pi 4. Okay, now after that, we need to know how many pi electrons we see in here. So how many pi electrons do you see in total? How many pi electrons do you see? 8? 4? It's actually 4 because each of the carbons in the double bond is going to give you 1 pi electron. Each double bond gives you 2. But we're looking at each of those carbons separately. So again, each carbon, part of the double bond, it gives you 1 pi electron. Why? That's how we make the little double bond in here. It's made of pi electrons. So far we just have 4 pi electrons. Okay, so far we're good. So this is a part where it's going to look like in general chemistry. So hopefully you guys remember how to fill out your orbitals. You always start from the lowest level of energy. I know it's not everyone's favorite. So we're going to start in pi 1. We're going to fill out that orbital before we start moving on up to the next energy level. So I have 2 electrons, so it's filled. So now I can go to pi 2. So there's my 4 electrons. So far we're good. Makes sense. Pretty easy to follow. Okay. Now, we need to use more labels for the different orbitals. So in this chapter, you're going to see bonding, non-bonding, and anti-bonding orbitals. Now, according to the little cheat sheet that we have in here, the number of anti-bonding orbitals needs to equal the number of bonding orbitals. So in this case, if we go back to the diagram, we know that we have 4 orbitals. That's an even number. So I know that the 2 at the bottom, pi 1 and pi 2, they need to be bonding. And then anti-bonding is just going to be pi 3 and pi 4. You have the same exact number of orbitals between anti and bonding. So far, does that make sense? So remember that the number of orbitals for your anti-bonding and bonding need to equal each other. That's why in this case, because we have an even number of orbitals overall, 4, we're going to have 2 of each. That's all it means. Okay, now, next label, and the important one, it's the one that is color-coded, HOMO and LUMO. Now, for that, we need to know the full definition of those guys, which are right here. So HOMO is going to be the orbital with the highest energy that's occupied. Now, to be occupied, you need 1 or more electrons, but minimum requirement is 1 electron. Now, LUMO is the complete opposite. It's the lowest in energy that doesn't have any electrons. So knowing that, again, we go back to the diagram. That's why pi 2 is going to be HOMO. It has at least 1 electron, and it's the one with highest energy. LUMO is pi 3 because it doesn't have any electrons, and it's the lowest one in energy. Now, so far, any questions on the ground state? Pretty simple. We're just labeling things. We're drawing out our electrons. That's it. Now, all of the labels that we just had, including pi 1 through pi 4, bonding, anti-bonding, HOMO, and LUMO, they are going to be transferred the exact same way in the excited state, okay? No labels are going to be changed. Now, to go from the ground to the excited state, what do you think is going to happen? What's going to happen in the excited state? Say that again? Yeah. So pretty much what happens between ground and excited state is that UV light is going to be shined into the molecule, and that's going to excite it, of course. So the transition is always going to be from HOMO to LUMO. One of the HOMO electrons is going to jump up to LUMO. So that means that so far, pi 1 still has 2 electrons. Pi 2 has 1 electron, and pi 3 has 1 electron as well. Okay, that's the excited state. Okay, so far, questions on that? Make sense? We're just moving up 1 electron. That's it. Now, next thing that you're going to have in every of the molecules that we're going to talk about today, you have a little chart that you should fill out. Why? Because some of the questions that you're going to get on your exam or quiz is that he's going to give you the name of the specific molecule. He's not going to draw them out. So you need to know how 1,3-butadiene looks like. So the question could be, in 1,3-butadiene, how many pi electrons do you see in the LUMO orbital in the excited state? It's just 1, exactly. So the questions that you're going to get on this topic are just going to be words. That's it. Your answer choices are going to be based on numbers. Simple as that. So that's why you should start knowing how to draw out your energy diagrams. And that's it. That's how you figure out the different numbers. So for that, I'm actually going to give you guys 1 minute, 2 to 3 minutes to fill out the chart with all of the numbers based on the diagram here. It should be pretty simple. We just went through everything. So again, you guys have 2 to 3 minutes to fill out the chart with all of the numbers. And again, it should be pretty simple. We already have the chart. If you haven't scanned the QR code, please do so right now. Okay, hopefully we got our answers pretty fast. So now I'm gonna make you some random questions. Okay, so you should be answering those with the chart that you just filled out. So specifically, we're gonna be looking at the ground state for now. So in the ground state, how many HOMO electrons are you gonna see? It's actually gonna be 2, not 4. Because remember, we're just looking at pi 2. Pi 2, it's the only one that's HOMO. What about, again, ground state, but how many LUMO electrons do you see? 0, nothing. Okay. How many non-bonding orbitals do you see? 0, exactly. We didn't talk about those guys yet. How many bonding electrons do you see? 4, beautiful. How many anti-bonding electrons? 0, and then non-bonding, of course, it's still gonna be 0. We didn't even talk about that one. How many pi electrons in total do you have? 4. Does that apply for both ground and excited state? Yes. Yes, it does. The total number of pi electrons stays the same in both ground and excited state. Now let's switch it to the excited state. In the excited state, how many HOMO electrons do you see? Just 1, because remember, one of them moved up. So how many LUMO electrons do you see? 1 as well. How many anti-bonding electrons do you see? Just 1. How many bonding electrons do you see? 3. And then for both ground and excited state, how many bonding orbitals do you see? 2, which is the same answer for anti-bonding. So pretty simple. As long as you know how to draw out your energy diagram, you should be able to answer all of the questions that he might throw at you on the exam. Yes. For these ones? So those ones are basically the lines that we saw in here. It's basically just asking for how many bonding orbitals do you have. So we only have pi 1 and pi 2. And then for anti-bonding, we only have pi 3 and pi 4. Because remember, the number of bonding and anti-bonding orbitals needs to be equal to each other. So the answer should always be the same. Okay, so far, questions on the first molecule. So far, how do we feel with this theory? Pretty simple to follow? Okay. Now let's move on to the next common example that you're gonna see on the exam. Your allyl cation. So remember, we start the same exact way. How many sp2 carbons do you see? 3. 3 or 2? Why 3? Exactly. So at this point, if you are a little unsure on whether they're going to be sp2 or not, just ask yourself, can it participate in resonance? If it can, it is sp2. So in this case, yes, we have 1, 2, 3. We have 3 sp2 carbons. So what did that mean? That's the number of orbitals. I have 3 orbitals. Simple as that. So again, that represents the little lines that we see in here. Pi 1, pi 2, and pi 3. Simple as that. Now, how many pi electrons do you see? Just 2. Remember, the cation, it's lacking electron density. So there's only 2 pi electrons. So once we start filling out, only pi 1 is going to be occupied. Now, we have our labels from pi 1 to pi 3, but now we need to look at bonding, anti-bonding, and non-bonding. Now, keep in mind the same rule. The number of bonding orbitals needs to equal the number of anti-bonding orbitals. That's why we only have 1 of each other. Exactly. So whatever you have left over, whatever space filler you have in between, that's always going to be non-bonding. Now, non-bonding is always present whenever you have an odd number of energy levels. Okay, so we have 3 levels. That's why we have non-bonding present. So far, does that make sense? We're good? Okay. Now, we know HOMO and LUMO. HOMO is just the highest in energy. That's at least with one electron, so that's why pi 1 is HOMO. LUMO is always right next to each other. Sorry, right next to HOMO, so that's why pi 2 in this case was LUMO. Now remember that every single label that you put in the ground state transfers over to the excited state. Okay, it stays the exact same way. So now this time, I'm not gonna show you how the excited state because it should be pretty simple at this point. And I'm gonna give you again 2 to 3 minutes to fill out the chart, and then we're gonna do rapid questions. No, they are not gonna correlate specifically to each of those carbons being pi 1, pi 2, or pi 3. No, doesn't have a correlation. It's basically just indicating the energy level. That's it. Okay, do we have our answers? Okay, now, this time we're gonna start with the excited state. How many HOMO electrons do you see? How many LUMO electrons do you see? 1 as well. How many antibonding orbitals do you see? We see 1, yes, and that applies for both excited and ground state. Yes, question. So let's look at our little diagrams in here. So we got the ground state. So to go to the excited state again, some UV light gets shone in there, and one of those electrons jumps up from HOMO to LUMO. So that's why each of those has 1 electron only. Questions? Okay. How many non-bonding orbitals do you see? Only 1. And that applies for both ground and excited state. Same goes for bonding. How many electrons do you see overall? 2. How many antibonding electrons in the ground state do you see? What about the excited state? 0 as well. How many non-bonding electrons in the ground state? How many bonding electrons in the excited state? 1, and then this is the rest. 2 and 0. Okay. Questions on the theory. Make sense? Yes. The ground state and the excited state are not happening at the same time. We're starting with the ground state. Everything is this way. So for the excited state, the only thing that happens is that you shift whatever electron you had in the HOMO orbital up to LUMO. This is just a brief moment. It's a temporary state for the molecule. That's why we only take this guy up to LUMO for the excited state. Yes, that's the same pattern that we saw in here. Again, we just take one HOMO electron up to LUMO. That's it. That's what you're always going to do. HOMO to LUMO. There's nothing in the non-bonding orbital for the ground state. Yes. Yes, it's always going to be lower in energy. Okay, so far, yes, question. It's only one electron, yes. At least for this class, it's only going to be one electron. Okay, so now let's look at the anion. So this time, you guys are going to do it from scratch. So you guys have 5 minutes to fill out the energy diagrams and the chart as well. So again, 5 minutes in total. Okay, so far, how are we doing? Pretty good. We all got our answers. Do we still need 1 more minute? Okay, looks like no. So let's just go through it. So what's going to be the first thing that you're going to look at? Exactly. How many sp2 carbons do you see? 3. Simple as that. We have 1, 2, 3. So 3 sp2 carbons equals 3 orbitals. How many pi electrons do you see? This time it's 4 pi electrons. One, and those 2. So again, you just start filling them out on your orbital. And again, this time I have a non-bonding orbital present because I have an odd number of energy levels. Okay, that's all it means. I have level 1, level 2, level 3. Remember, bonding and anti-bonding need to equal each other. So if you have one of non-bonding, if you have one of bonding, you need 1 of anti-bonding. If you have 2 of bonding, you need 2 of anti-bonding, so on and so forth. So whatever's left over right in the middle, that's always going to be non-bonding. You're always just going to get 1 non-bonding orbital, only 1. Now, you have to label HOMO and LUMO because remember, that's not going to be provided for your exam. HOMO, again, is just the highest in energy that has at least 1 electron. That's why pi2, the non-bonding orbital, is HOMO. LUMO is just pi3, doesn't have anything. So in the excited state, how many electrons is pi1 going to have? It still has 2. I never touched it. What about pi3? Now it has 1. Pi2, 1 as well. Just remember, I only take 1 HOMO electron up to LUMO, and that's it. So again, if we filled out the chart, this part should be pretty simple. So how many HOMO electrons are you going to see in the excited state? What about the ground state? How many non-bonding orbitals do you see? 1, and that applies for both ground and excited state. What's the total number of pi electrons? 4. How many anti-bonding electrons in the ground state? How many anti-bonding electrons in the ground state? 0. What about the excited state? Now it's 1. How many bonding electrons in the excited state? Ground state? 2 as well. How many electrons in the non-bonding orbital for the ground state? 2. So in the excited state, there's only 1. And then if we fill out the rest, just 1, 1. And then how many LUMO electrons in the ground state? Beautiful. Okay. Questions on the molecule? Make sense? Okay, seems like we're good. So again, yes. Exactly. It's like a little sandwich, yeah. It's like a little sandwich. If you look at it, it's like a little sandwich. Show me your drawing. The line. That's gonna be one. Again, MO is a molecular orbital. So they're asking for anti-bonding ion count. It's one. That's how you correlate. Nothing in here is gonna be provided. The only thing. That's it. It is a good question. It is a good question. I'm not quite sure what non-bonding means. Anti-bonding is just, damn. Yeah, so if we go back to Orgo 1, we talked about anti-bonding orbitals with SN2 because of the backside attack, right? We remember that portion? Okay, so the anti-bonding is literally just 180 degrees apart from the bonding. It's the complete opposite. Let's say that it's the antagonist of the orbital. The non-bonding orbital, I have no idea. That one I do not have idea. It's basically like, so we see the little A looking structure, right? That's your orbital. So let's say that the one that has the electron here, the first half, this part, it's bonding. The second part, the part that's empty, it's anti-bonding. Yeah. It's just the empty space. Yeah. Yeah, it's just the empty space. Technically, they can flip around depending on what you do to the molecule, but let's try to keep it as simple as we can. But again, the drawings, the energy diagrams, the chart, I'm providing it just for your benefit. So you guys can take a look at it. In the exam, nothing of that is going to be provided, not even the drawn out molecule. The only thing provided is just the name. So he can say 1,3-butadiene, allyl cation. That's the only piece of information you're going to get. And that's it. Yes. Yes. The anion provides 2 pi electrons. So yeah, let's do a little cheat sheet in this case. So whenever you have a carbocation that doesn't give you any pi electrons, if you have a anion that gives you 2 pi electrons, what if you have a radical? Just one. That's it. Yes, the back. Didn't I post them? Is there not posted yet? Don't worry, they're gonna be posted. They're gonna be posted, so yeah. Relax. You guys can just pay attention, not take notes if you want. Just pay attention. You can always look at the recordings, so. Yeah. Okay, so far, questions on the anion example. We're good? Now, very last one is gonna be your radical. So this time, actually, let's do it on the spot. So let's see how you guys do. So we're just gonna start with the random questions automatically. Maybe you already solved it if you had extra time, but how many pi electrons are there in total? 3. Is that for ground and excited state? Exactly. How many? Yes. Total number? No, that's just a trick question. It should be the overall, it should be the same. Yes. How many antibonding electrons in the ground state do you see? Beautiful. What about the excited state? Now it's going to be 1. How many homoelectrons in the excited state? None. Beautiful. Ground state. How many LUME electrons in the ground state? Excited. Beautiful. How many non-bonding orbitals do you see? That's the one that was provided. It's 1. What about anti-bonding orbitals? And same for bonding. How many bonding electrons in the excited state? Ground state? 2 as well. Non-bonding electrons in the excited state? Ground state? 1. Okay. How easy was that? Wasn't easy? Okay. So in this case, yes, technically you can skip it because it depends on what's presented in the molecule. So we know that those guys are your 3 orbitals, right? We have 1, 2, and then 3 electrons in total. So let's just start drawing them out. In this case, pi 2 has the minimum qualifications to be HOMO, highest energy that has at least 1 electron. So pi 3 in this case, it's LUMO. Okay, so far we're good. But same process happens all over again. To go from ground to the excited state, you grab whatever HOMO electron you had up to LUMO. So yes, technically, your non-bonding orbital in the excited state is going to be empty. It doesn't have anything. So yes, basically we're skipping 1 orbital in there. But again, it depends on what kind of molecule you have. So questions on the radical. I know that we went pretty fast on this one, but did anyone get the answers relatively easy, relatively fast without drawing out the diagrams? Not really. I just see 1 yes. Okay, that's okay. It just takes practice, guys. Question. If it's a regular carbon, that means that it's sp3. So it does. You're saying like a molecule like that? Yeah, this guy, it's sp3. It's not going to participate at all. So that even simplifies it even more because you wouldn't have pi 3 at all. Okay, so far. Question, yes. It depends with the different molecules we have because we have to see which one correlates to the definition of each of them. So HOMO, it's the highest in energy that has at least 1 electron. It's the highest energy that's occupied. So depending on what kind of molecule you have, it's gonna vary. Now, if you're able to determine where HOMO is, LUMO is very simple. It's always right on top of HOMO. So you don't even have to worry about memorizing the 2 definitions, let's say. But LUMO, it's the lowest in energy that doesn't have anything at all in it. So again, that's gonna depend on the molecule that you have and how you're drawing them out. So for the radical, let's say, pi 2 was HOMO. But for the cation, pi 1 was HOMO. Again, it depends on which specific pi orbital qualifies for the definition. Okay, so far, questions on that? Did it make sense? The top one, this one? Okay, now, hopefully we're starting to feel a little more comfortable with this theory. Remember, in the next page, that's where you have your little cheat sheet, okay? On how to draw them out, what each of the orbitals means, how many are there. And please keep in mind that every single label that you find in the ground state transfers over to the excited state. Meaning that whenever you get any questions, please just start drawing out the ground state. Do not jump right ahead to the excited state because you're gonna get the labels wrong that way. So let's just finish with this question in here, which is very similar to what you're actually gonna see on the exam. What is the most favorable energy transition for 1,3-cyclopentadiene? How would we answer that? There's 2 different answers. What is the most favorable energy transition for 1,3-cyclopentadiene? What's the transition that happens between any ground and excited state? You're moving from HOMO to LUMO. So that's going to be the answer for any molecule that you're seeing there. Simple as that. Whenever they're asking for the favorable energy transition for any molecule, is always going to be from HOMO to LUMO. Now, specifically this molecule, if he doesn't give you the answer choices as HOMO and LUMO, he might specify from pi 1 to pi 2, from pi 1 to pi 4. He's going to give you different answer choices like that. So in this case, we just start looking at the little molecule in here. So it's that one. Is that molecule fully conjugated? What do we think? Yes or no? I see one yes. I see one no. What's the requirement to be fully conjugated? Everything has to be sp2. In this case, this little carbon in here, it's sp3. So it breaks that rule. It's not fully conjugated. So let's add one more thing to the theory that we just learned. The theory that we just learned is specifically for molecules that are non-cyclic. And if they are cyclic, they do not need to be fully conjugated because the theory changes once you have something that's cyclic and it's fully conjugated. We're going to see that later on in chapter 14. So for now, do not worry about it. But in this case, this molecule, how many orbitals do you see in total? 4. How many pi electrons do you see? And 4 pi electrons. So would the energy diagram resemble any of the molecules that we just did? Which one? 1,3 butadiene, exactly. So if we go back to this little guy in here, the same energy diagram that you see for ground and excited state is going to apply to the one that we just talked about, 1,3 cyclopentadiene. Same exact diagram. So in this case, exactly, it's going to be from pi 2 to pi 3. Simple as that. So those are your two possible answers. Yes. For now, just worry about the 4 molecules that we talked about. The normal conjugated diene, the allyl cation, anion, and radical. Yes. Yes. The rules should be pretty similar for the cyclic fully conjugated ones, but there's going to be a few tricks here and there. But practically, we're already finished the theory in here. Before you pack up, how comfortable do you feel with this theory? Mid? Not so good? Good? More practice? Okay. Now, when you go in lecture, you're going to see a lot of drawings from your professor. So please do not get overwhelmed. Do not get scared. Do not get overwhelmed. The theory can go really, really deep. So again, just try to keep it simple. Draw out your own diagrams, okay, from scratch, always, so you can follow along in lecture. So that's it, guys. I'll see you guys Monday. It's not a holiday. Monday, it's not a holiday. So there's still class. Yes, Tika. For bonding, it's just one because you only have one line of bonding orbitals. They should be the same here. They should be one. Yes, we only have one bonding orbital. Basically, how many bonding lines do you
So
see?
you're looking here for this,
Yes, exactly.
and for this.
Everything, it's the same way. I'm just changing the different names. Non-bonding, anti-bonding. So I'm just looking at, for non-bonding, I'm just looking at this. For bonding, I'm just looking at this guy. Anti-bonding, just at that. And I know that the answer should be the same for ground and excited state because every label just transfers over. No problem, guys. Take care.
So I got a little bit confused with this. This part, I was like,
Yeah, it's such a small change in the words that we're using. We're going from electrons to orbitals, so always be careful on what specifically they're asking you for. But yeah,
All right, thank you.
no problem.